So we're talking about lightweight lock contention in our Postgres replica databases, in how we're coming up, how I think we're close to a tipping point every weekday during daily peak. So this is an incident where we crossed the tipping point, and you can see this is kind of a high-level generic representation of our connection pool becoming saturated, obviously right here. That's an effect, not a cause. It cascades to the rest of the application stack in kind of the usual way when more people want to run queries than the system can handle. So I'm going to dig from here into some causes. So this is the graph I want to show, but I want to show a wider time span. I'm going to try for 2 weeks. We'll see how long it takes to render. There's a lot of interesting things to show, and I'm going to resist the temptation to go into to go too deep into the tracing. That's not it. Goodness. I think I may have closed my tab that had the data I wanted to share, but this will be, oh, this is 2 weeks is not quite enough. Let's go with 4 weeks. So while that renders. Okay, so this is our incident, and what we're looking at here is a few times a minute we look at a snapshot of a standard Postgres catalog view called pd_stat_activity. It's got 1 row per Postgres backend, and some of the really interesting data it gives is what that backend is currently waiting on, if anything. If it's active and it's running on CPU and it's not currently in a wait state, then there won't be a value for a wait event. But in this case, we're filtering to when the wait event is the lock manager lightweight lock. This particular, so lightweight locks in general are, let me take a step back. Just because the vocabulary can be a little confusing. Normally, when you talk about database locks, we're talking about what formerly is called heavyweight locks. This is a lock on a table or an index that says, hey, I'm using this table, please don't change the schema at this very moment, for example. When we need to update data structures in-memory data structures safely concurrently, we'll use kind of a mutex mechanism called lightweight locks. And in this case, the specific flavor of lightweight lock that we're talking about is the one that guards the hash table that records who has heavyweight locks, and that's why the lightweight lock is called lock manager. So just want to clear up the terminology because that can really throw people off. So as that suggestion kind of implies, when you see contention over the lightweight lock that guards access to the heavyweight lock, what we're really seeing is contention over the frequency with which backends are trying to change the state of what tables and indexes they have locked. So the resource that we're starving for here is access to the lightweight lock, to this particular lightweight lock, and it's specifically driven by how often we acquire and release heavyweight locks on tables and indexes. By extent, I'm kind of jumping into solution before I've gone through the whole problem, but I'm gonna roll with it. By extension, this means when we partition a table, for example, if we partition a table into 10 pieces, we now need 10 times as many locks, and it's not just locks on the table; it's locks on all of the indexes of the table. So if you run something like select star from projects where ID equals 1. You're going to acquire the lock on the table and every index for that table, and each one of those heavyweight lock acquires requires acquiring and releasing one of the lock manager locks. There's only 16 of these locks. Every table and index is guarded by an arbitrary one of those 16. It really kind of hashes the lock tag and does modulo 16 across them to deterministically choose which of the 16 lock manager LW locks is acquired. But what we're working up to here is things like schema changes, where we do partitioning or adding indexes, or something even less obvious, where we perhaps change some application code so that it needs to do an extra join, or similar kinds of things, where we do refactoring on a query that to split it into two queries instead of one. If those queries happen in separate transactions, which is very likely for the way that we manage our connection pooling, we'll have to acquire and release those heavyweight locks separately for those two queries. So some very benign and often helpful changes on the application side and the schema side can alter the rate of acquisition of these lock manager lightweight locks. And that's, I think, what we don't have a good way to measure at this point. Query rate is the best surrogate that we have, and it's not enough. When I say it's not good enough, what I mean is during the incident, we knew that each replica DB was getting about 60,000 queries per second. When we reintroduced the two additional replicas, that went down to about 50,000 queries per second, and we're okay at that point, and we were not okay at the 60K. But historically, a month earlier, we had been perfectly fine at 60K. And I think the difference is the rate of how often we acquire these lightweight locks, the lock manager lightweight locks, has probably increased in the meantime due to some change that normally would have been benign if we hadn't been at the tipping point. So
can I interrupt you and ask some clarifying questions?
Yes, go for it.
Because I want to keep up with what you're saying. So these are replicas, they serve read traffic.
Correct.
So read queries still require heavyweight locks.
Yes.
These are not locks that are happening because we're modifying something, but read queries require them.
That's true. I should also clarify that the same thing happens on the primary database, but what we starved for is the replica database, was on the replica databases, but the primary is just as susceptible. So
yeah. Any read query we do taking heavyweight locks?
Everyone, yeah.
Yeah. Okay.
There's there's several modes the lock that heavyweight locks come in, and the weakest mode is called access share, and it only conflicts with access exclusive when we're making schema changes like adding a column to a table or whatnot.
Yeah, but even if there's no conflict,
yes,
the query takes the lock and releases the lock, and it's updating this central one of these 16 lock manager structures, and that's where the problem happens.
Yes, yeah. Exactly.
Okay,
there's a big caveat that I'm trying to find the right place to add. There is, because this is a known contention point, historically Postgres introduced what it calls a fast path for trying to acquire a heavyweight lock that essentially says under the right conditions, we can avoid having to update the shared memory data structure and only update a local hash table instead. And I'm going to gloss over the requirements for it. I just want to mention that this exists.
Yeah,
and
it sounds like this is a known problem, because otherwise they wouldn't have split that data structure in 16 pieces either.
That's right. That's right.
Yeah. Okay.
I remember before they split it.
Yeah. So naively, every query needs to take a heavyweight lock, and they've done lots of optimizations to reduce the pain of this, but it still happens. Yes. And then the other problem you're saying is that depending on things like joins in queries, you don't know how many heavyweight locks a single application query needs. So you can get unlucky and run a bunch of queries that don't hit an optimized path and that do need a whole lot of locks. And then we end up in this zone where we have to update this one of these 16 things too often, and we get contention.
Yes. Great summary. Yes.
Thanks.
Yep, absolutely. So back to the graph. There's two visual aids I wanted to kind of talk through. One of them is this graph, where we can see that this is obviously the incident that we're talking about. This is a stacked graph grouped by replica. We're looking only at the vertical axis is counting how many backends were at the moment that we polled the state. We're stalled waiting for this particular kind of lightweight lock. If we go to just a line graph, we can see that on the most badly impacted replica, there were 659 stalled Postgres backends, all of which were waiting for this type of lock. And this is really, really serious. This is essentially practically all of them were stalled waiting. This is max over time, so we're looking at the worst sample in a 5-minute window. But I guess it's also important to remember that we only poll a few times a minute, and these locks normally these lightweight locks are acquired and released on a scale of microseconds. So there are many of these events that we're not actually witnessing. So we can take this as a very small representative sample of the amount of contention that's happening. And I wanted to mainly mention that because these other points in time, these other kind of normal weekdays, also exhibit this kind of contention, and we're only seeing the tip of the iceberg for them as well. From a practical matter, it's normal to have contention over locks and lock-like data structures for short periods of time. It's a really only problem when the contention escalates to the point where it impacts latency and limits throughput. And the difference between the workload on this terrible day and these more normal days wasn't too huge. It really was just that we pushed a few more percentage points toward these replicas by taking a few of its peers out of use. Like we went from about 60,000 to 50,000 to kind of back off during this day, which is the same thing that this adjacent day was on. And you can see that we still have contention on those days when we've got 50K queries per second hitting the replicas, but it's tolerable. We're not violating the apdex. I mean, most definitely we're violating the apdex on this day. That doesn't mean 60K queries per second is untenable. It just means with the current mix of lock manager acquisition rates and hold duration, we are in a dangerous position for having this come back, especially if we take one or both of those old replicas away. I think most of the folks here are probably aware, but we're all of these database servers are running kind of old VMs. They're the N1 machine family, and we're wanting to switch them to N2 or the AMD variant of N2. And these last two ones, the node 101 and 121, are specifically those newer candidates for machine type. And there's been some hopeful talk about maybe we'll be okay when we upgrade all of the replicas to, or rather all of the Patroni nodes to be these newer machine types. They definitely performed better during the incident, and I'll kind of show here that we didn't have any samples where they were overwhelmed. But I also want to point out that they also only got a slight bump in the query rate, and we know that they have higher throughput in terms of instructions.
I thought you said they weren't participating in the incident, and the incident was resolved by bringing them back.
Right. So yeah, sorry, I kind of glossed over the details. So prior to the incident, let's see. So 04 is the primary, so I'm going to leave it out of the mix here. So prior to the incident, we had 01 through 03 and 5 through 07, and those are the old 6. And then 101 and 102 were the 7th and 8th nodes. We've removed nodes 06 and 07, which are old nodes, the day before the incident during APAC shift. And
okay, I thought we removed the new nodes we were testing with. We removed some old ones.
That's correct. Yes, and then we put the old ones back in service to prevent a recurrence of the incident the next day. Yeah.
So why did the new ones do so much better?
I think they did slightly better, and it was just barely enough. So but that's a fantastic question. So and that's kind of where I was going. So so in terms of So for purposes of this conversation, I'm going to talk about CPU speed really in terms of instructions per second. Assembly instructions per second. So I'm totally making these numbers up, by the way. If we say that these N2 machines were able to achieve, say, 10% or 20% more instructions per second, then the amount of time spent holding each occurrence of holding this lock manager lightweight lock would be proportionally shorter, and therefore less likely to be contended. So I think that this gives us a marginally larger headroom, because you only get contention when you have when the rate of acquiring a lock times the mean duration of holding the lock kind of runs up close to the saturation point when and I think that we're just barely avoiding that under normal circumstances on the old nodes, and the new nodes have a higher instruction throughput, and so they are a little bit further away from that 100% of the time the lock being held. Does that make sense?
Yeah, thanks.
Mm-hmm.
To be clear,
that's
anything we're looking at here is suffering from this like the resolution problem that you brought up. So even the new nodes that barely show up when you highlighted them could be super close to the tipping point already. They're just a little bit farther off than the old ones.
Yes, exactly, and that's why we can't use this metric alone as a predictor for hitting the saturation. We only see spikes on this graph once we've reached that saturation point. So we could be 90% of the way there and not see anything here, and it's not till we actually cross that line. And this is very susceptible to I don't want to call them microbursts, but like, small scale variations in the amount of in the lock acquisition rate. Can kind of cause spikes on this graph and lead to contention. So the other thing, I really do need to find my other issue. Why did I not keep that tab open? I think this is, yeah, okay. So this is just kind of walking through the effects of the saturation. I'm going to gloss over that. This is the graph we were just looking at, kind of zoomed in on that day, so it's a little easier to see the shape of it. This is, I think, a 2-week timeline, so we can see adjacent days and how it looks there. It's just finer grained version of what we were just looking at. So the other thing I wanted to show is, no, not that one. Yes, this one. Okay. So I mentioned that the lock manager lightweight locks are acquired on a microseconds timescale. This is, so I'm going to gloss over the details of how I captured this, unless someone's interested, because I find it very interesting, but I'm going to just focus on the data right now. So this is for a 10-second time span. We captured every time, we're capturing every time we try to acquire one of these 16 lock manager locks, and it's not immediately available. In other words, when it's contended. How long did it take to acquire that lock when it was contended? And this is the distribution we're seeing. So in 10 seconds, we had maybe 45,000 or so, or 50,000 or so points when it was contended, and most of them resolved in less than 4 microseconds. But some of them, the long tail is what really worries me, where sometimes we had and this was just a random 10 seconds, by the way. It wasn't during an incident. This was just, I got up and I ran my capture utility, and this was the result. There's a lot of variation in this long at different points in the day, and I've seen this long tail in production go several times higher, where we're waiting for several milliseconds to acquire the lock, and those are I suspect that those are the stalls that we're actually witnessing in the spikes that we were looking at on the other graph. So this kind of understanding the long tail, why we have these ridiculously long stalls, this is one of the open questions that I'd like to try to answer. And I've got a few hypotheses about what could be causing it, and some of them I've ruled out, and some of them are still kind of in the running. For a while, I thought that hyperthread contention may potentially play a role, and I think that's unlikely at this point because sorry, I shouldn't talk about discarded theories. So this is an open question, and but I guess the main reason I wanted to show this distribution is to kind of put some hard data in front of you, and oh, I forgot to mention these there's two lock modes that come into play with lightweight locks. There's shared mode where that's a reader lock, and exclusive mode that's a reader writer lock. So these lock manager locks are almost always acquired in exclusive mode. There are cases where it's acquired in shared mode, but the analysis that we've done here really highlighted that it's the exclusive mode where the contention's happening, and if we capture every event, every call to LW lock acquire rather than just the contended ones, it highlighted that we far more often are acquiring in exclusive mode rather than shared mode. So this is the mode to focus on, and it is unfortunately that means that contention escalates very quickly. I'll stop sharing now just because there's nothing interesting to see there.
Well, it sounds like we need more replicas.
Yeah, I think
which is what you started with.
Yes. I would ideally like to do a few things. If we can compose a metric that gives us a better predictor of how close we are, something that we could translate into a utilization percentage so that folks can see how close we are. I think this will make everyone much more comfortable in kind of planning out our capacity requirements, as well as being comfortable with being able to make query changes. Like if we make query changes or schema changes, like we know that some of our tables are too big, and we know that the solution to this is to partition them, and there are lots and lots of great benefits to doing this partitioning. But that is also something that can potentially increase the risk of this lock manager LW lock contention, particularly if we have any queries that don't do efficient partition pruning as part of the planning process. So
yeah, I was going to say the other thing you can do is not make those queries that don't hit the fast path, but how practical is that really? Because we're now talking about something very deep in the Postgres internals that very few people understand. I certainly don't. And we want all our application developers to make sure they hit these fast paths on a gigantic production database.
And we want them to use replicas. We don't want them to scare them away.
Yeah, exactly. And that's one of, I mean, to be perfectly honest, that's one of my biggest concerns, is making developers afraid to move queries off of the primary and onto the replicas. And it's super helpful for them to do those migrations, because we can scale out the replica fleet, and we can't scale a primary fleet without a major architectural change. So yeah, I want them to feel comfortable doing that very important work. I'm glad you mentioned the fast path again. I wrote, I'll put this in the issue, but I wrote up a really concise kind of bullet point list of what are the prerequisites for hitting the fast path, and many of our queries do. So kind of one of my ideas for follow-up is to try to identify queries that don't. Like one of the requirements is there's each backend has 16 slots for recording fast path activity, and if we filled up those 15 slots within the transaction, we can't use fast path anymore for the rest of the queries in that transaction. And effectively, that's, I mean, that's a hard-coded number. So,
but even if we can predict this, how do we get this information back to developers on time before the code is in production, causing an incident?
Right, exactly. So this is why this is one of the reasons why I feel like the right answer is just to have a big enough fleet that we don't have to worry about it.
Yeah, and to focus on good metrics so that we can do the capacity planning.
Yes, exactly. So that's kind of the way I'm leaning. Although definitely, I also kind of want to be able to give advice about how to construct the queries to like hit the fast path more often. But really, I agree. I don't think it's practical to expect everyone to become an expert in this particular really weird optimization goal.
Yeah, and
So
and even if they were, like, if you need to know, if it depends on the number of partitions we have, and if you're how many partitions you're ranging about, like, how do you even recreate a test environment where you can do that?
yeah, exactly. Like I think kind of crystal ball time. I think one of the easiest ways for us to run into this problem is to add an index to a frequently accessed table, and perhaps some set of existing queries already were like perhaps joining that table to one other table, and the total number of indexes across those tables. So you've got two tables, and if you've got 14 indexes on those tables, and we add one index to either of those tables, guess what? You no longer qualify for a fast path. So now every time we run that particular query, it has to go to the shared memory lock table and compete for these LW locks. And this is no one's fault. It wasn't even a code change, it was a schema change, or vice versa. We introduced a join through a code change, and there was no schema change, and we have the same outcome. This is not something that people are going to predict very efficiently. So, and the code changes either roll back.
Only show right after the tipping point. So
exactly,
chances are like it could live in our code base for a year, and we grow, and then suddenly, bam, like we had.
You wouldn't even show it if you did like a small traffic share on a small bit of. You'd only see it until it's a problem. Is that fair?
Yes, that's exactly right.
Hey.
Which brings me to my next question, Matt. You showed the eBPF analysis that you did there. Is there a way we can, because that's expensive, and you explained that to me.
Yes.
Is there a way we could do that cheaply somehow and get that?
I'm gonna show why the answer is no. Bob, you may have seen this, but this is cool enough that I think it's worth 60 seconds if I can find the graph in that short amount of time. Oh no, the Zoom widget's in the way. Is this it? That's not it. That's it. Okay. Okay. So the way BPF instrumentation works is you want to catch calls to a function. Say the entry to a function like LW lock acquire. The way that works is in the binary, the first instruction that's part of entering that function gets replaced with a single byte instruction called int3. That's effectively a call out to an interrupt handler. Every call to that function is going to hit this instruction, and whatever the other instruction was, whether it was a single byte or a multi-byte instruction, we will run that instruction after calling the hook that the interrupt handler is handing off to. So what we're seeing in this trace is we're catching we're observing with perf-based CPU profiling that's capturing a stack trace from our Postgres processes every 99 times a second. So this is just standard CPU profiling on a timer basis. And I ran that for 60 seconds. During that 60-second window, I also ran the 10-second BPF tracer, extracted only the stacks where that tracer was active, or where we're calling the LW lock acquire function. And you can see that this is just proportionally on the graph. This is how much time we spent in LW lock acquire normally. This is all time spent in the interrupt handler trying to transfer control flow from normal user space to the BPF program I wrote. And this is the actual BPF program I wrote. So there's no way we can optimize away this giant chunk of time that's just spent in the interrupt handler.
That's only a sixth of the
time
that was running, and it's already
it's really terrible user space probes, because you have a user space function and you turn it into a system call.
Yeah, that's
with,
right.
with the context switch in it, because eBPF runs in the kernel. So you cannot run your BPF program without going into the kernel and back. So like you never want to do extra function calls, and there's a reason this is it's almost always terrible to make a user space function into a system call.
Yeah, and it's just unfortunate that in this case the function we need to trace is called frequently. Like you can get away with that overhead for
Yeah,
low frequency
that's true.
calls,
If it's something like you're doing writes on a socket, then that doesn't happen that often, and it's a system call anyway. Actually, then you wouldn't even
yeah,
have to because it is a system call. So
it's a
you
system call, right?
hook it on the kernel side.
Yeah, yeah, exactly. So that's why we can't do this approach. There are kind of a few other kind of models we could maybe do. So this is highly speculative and may not actually be practical. Just to kind of preface it with a caveat. The two kind of harebrained ideas I'm entertaining right now is one. We could do the lightweight CPU profiling with perf that we usually do, and count how many times we observe in that timer-based sampling. How many times do we observe LW lock acquire being called? The big caveat is that doesn't tell us which kind of lightweight lock, and we definitely there's like, I don't know, 80 or so different kinds of lightweight lock, so it's not always going to be this kind. But we can infer from the rest of the stack because
you can see it in the frame, right?
Yes, exactly.
You can see what the caller was, so that you probably know that which lock it was acquiring.
Yes, yeah. I think so. So that's a maybe. It's definitely lightweight enough to do. It may be useful or it may not be useful. I'm not sure yet. I haven't tried it.
Well, the problem with any of these things is if you want to have a utilization, like what is 100%?
Yeah. Right.
Okay, you can also, if we were able to get those histograms, then you don't want high tail latency, but like what is the worst it can get? Or if we could measure how many things are waiting, how long is the queue allowed to be?
Yes. Yeah, exactly. And the wait event sampling that we're doing from PG stat activity tells once we cross that line of having contention, we can kind of estimate it from there. But before we reach that point, it's really hard. So the other harebrained idea I have is that also may not work out. There's another catalog table called PG locks that's just describing what heavyweight locks are currently held by open transactions. And one of the fields it includes is, did we acquire this lock through FastPath? So that can let us differentiate between whether we're acquiring the lock on FastPath or not. Holding that in the same way that we pull PG stat activity a couple times a minute may not give us a lot of insight. I'm not really sure, but I figure it's worth a shot. So that's the other thing on my list to try out and see if we can A, get useful information from it, and B, come up with a way to make a metric out of it. So that's as far as I got so far on ideas for how we can make a metric to kind of measure utilization, or at least approximately.
At least there you can naturally define a percentage, because
yeah.
But I'm not sure if it's a useful percentage, because you could say how many of the rows in there are FastPath or not.
Yeah. And how many of the backends are holding more than 16 that were not on FastPath? Or I guess that's a little silly because we are, never mind, forget that. If it wasn't FastPath, it doesn't matter why it wasn't FastPath. It wasn't FastPath.
Yeah. I mean, number of locks that is not FastPath. At least it's simple to define. I think that is a good thing that it has going for it.
Yes. Yeah. So that's kind of the whirlwind tour. Hopefully that was interesting, and I think I mean, kind of circling back to what we do about it, I think it's important to get a utilization metric, and it's also important to avoid incidents. And I feel like we're currently in a dangerous spot where if we lose a replica, whether it's planned or unplanned, we'll be in a state where we could potentially cause it, have an incident. So I think we should add at least one additional replica, like nowish.
There's one more question I wanted to ask about this.
Yeah.
You said this is an old problem in Postgres that they've been optimizing over time.
Yes.
What do other people do about this?
Yeah.
So other big Postgres sites that run into this bottleneck, what do they do about it?
Well, the last time I ran into this bottleneck at a previous company about 6 years ago, we did actually rewrite. We identified which queries were the greediest consumers, and we rewrote them with this as an optimization goal, reducing the acquisition rate for the lightweight lock. In our case, we knew what the candidate queries were, and it was a small enough number that we could afford to manually look at them and do some tuning on it, and that got us most of the way out of the pinch. And I also built a custom build the Postgre that gave us more lightweight locks in the pool. And a few versions later, the community did the same thing, which is why we have 16 now as a standard. I guess that's
is adding replicas something people do?
Yeah. Yes. I think I've seen. I'll see if I can dig it up. I think I saw a write-up from one of the Postgres as a service clones. It might have been Aurora, but I can't remember for sure. That was talking about how to interpret contention over lock manager lightweight locks in particular. So this exactly the problem we're talking about. And they were talking about increasing the number of replicas, which they're Postgres as a service, so they make more money if you run more replicas. So I kind of take that with a grain of salt, but it is good advice also. So yeah. Great question. I guess that's kind of my half-baked answer is yeah, adding replicas and trying to optimize queries to reduce the acquisition rate. I guess like from our perspective, we do a lot of caching of query results. So from the application side, if there are frequently run queries that we could afford to cache more often at any of the other layers, that's another way to mitigate by just reducing the lock manager acquisition rate.
But it's kind of the same solution, right? It's fewer queries per box.
Exactly.
Yeah.
I guess that's it then. Anybody else have questions or comments? Cool. I've only documented about half the research I've done, so a lot of the flame graphs we looked at are not in the issue yet, but I intend to get them there today or tomorrow. So if you happen to want to see more of that, give me a ping or just wait a couple days. They'll be there. All right, gang. Thanks for staying late. See you later.